We will go on to a little different problem now. There are two tanks containing carbon dioxide. It says these two tanks are connected by a pipe with a valve. So, let us draw them as usual. I have a valve here. I am going to call this as tank A and tank B. Both are containing CO2. So, I have only one species, that is something which I will make a note of. One of the tanks contains 1 kg of CO2 at 70 degrees centigrade and 1 bar. So, let me call that as A. Mass in A is 1 kg. The temperature initially of A is 70 degrees centigrade and the pressure is 0.5 bar. And then I have tank B here, which contains 4 kg of CO2 at 20 degrees centigrade. I have two tanks, so I am going to write T1B here. Temperature initially of B is 20 degrees centigrade and the pressure initially of B is 1 bar. The tanks and the pipe are not insulated. Okay. So, since they are not insulated, it is possible to have heat interactions in both the cases. The valve is now opened and the gases are allowed to mix. So, initially I have these two tanks, both have the same substance, but at different temperatures and pressures. So, this is possibly a smaller tank. It has a smaller mass at a lower pressure. This has a higher mass at a higher pressure. The temperature here is higher, the temperature here is lower. So, but the pressure here is higher. So, what will happen as I open this valve is substance from tank B, I would expect it to come to tank A because the pressure here is higher and here it is lower. I do not know what the initial volumes are, they may or may not be the same. Once the valve is open, if you open the valve slowly, this process will happen slowly, and then at some point of time the pressures will equalize and then there will not be any more flow of these substances. The temperatures initially are different. Here the temperature is initially high, here it is initially low. Now, there can be, when these things mix, there is hot gas from here mixing with cold gas from here, they will reach some temperature finally. The final steady state temperature is given as 40 degrees centigrade. So, the temperature in both the tanks finally is 40 degrees centigrade. So, let me make a note of that here. We are asked to calculate the final equilibrium pressure and the heat transfer during the process. We can use an ideal gas model with gamma as 0.3. So, we want to find out the final pressure. The final pressure, we expect pressure in both tanks A and B to be the same because it is in equilibrium. We need to find out this final pressure, and we are also asked to find out the amount of heat transferred during this process. That is something we are going to find out. We have gamma as 0.3. CO2 is a triatomic gas. We expect this is supposed to be 1.3. I am sorry about that. CO2 is a triatomic gas. We expect it to have a gamma value of about 1.3. So, what we can do is try to find out all of these values. So, let me just write these things again because I am going to need them. So, I have 1 kg 70 degrees and 0.5 bar. Then I have 4 kg. I think I have 20 degrees centigrade and 1 bar. Let me just confirm that this is correct. Yes. Since we are assuming CO2 as an ideal gas, So, therefore, this expression P v equal to mRT must hold. Now, the value of R here is what we call as a specific gas constant, and we get it by dividing the universal gas constant by the molecular weight. The universal gas constant is 831.14.5 joule per mole Kelvin, joule per kilomole Kelvin. The molecular weight of CO2. So, I have carbon which is 12, oxygen which is 32. So, this is 44 kg per kilomole. So, the kilomoles get cancelled, I am left with joule per kg Kelvin, and my value of R over here is 188.96. So, I am going to round that off as 199 joule per kg Kelvin. So, this is the value of the gas constant for CO2. I am just going to call it R for the rest of this problem. At some point of time, I think I am going to need specific heats. So, I will possibly find them out here. So, CV is given as R by gamma minus 1, gamma is given as 1.3. So, that is going to be 189 divided by 0.3, which comes out to be about 630 joule per kg Kelvin, and I have Cp which is gamma times R by gamma minus 1, or which is also equal to Cv plus R. So, that is 630 plus 189, which is about 819. So, I have these values. What I am going to do is take both of these tanks together as my system. So, let me take the system as both of these together. So, the mass of my total system is 5 kg. So, that is the system finally. Initially, I can also take each of them separately. So, what I can do is I am asked to find out the heat transferred. I do not have a direct way of finding out the heat transferred because I do not know the temperature of the surroundings. But what I can do is I can find out any work done and any changes in internal energy and then use the first law. So, that is essentially what I am going to do. So, since I want to do that, I am going to try to find out the work as well as the change in internal energy. This system itself is stationary, it is not moving anywhere. So, there is no change in potential energy of the system. There is also no change in the kinetic energy, the system is at rest, velocities are 0. So, delta E, which would be a general change in energy, in this case is only delta U. So, that is all I need to find. Now, I can try to find out work. If I consider both the gas here and the gas here as my system, then I can try to see what the work would be. In order for work to be done, what we said is that we need three things. We need to have a donor system which can do the work, we need to have some receiving system which receives the work, and then we need to have transfer, so that there can be some energy transfer. If both of these together is my system, what I see is these containers are rigid, there is no deformation, there is no electrical or magnetic work or surface tension work or anything of that kind, there is no shaft, there is no shaft work. So, these are rigid systems. So, any transfer of gas from one place to another is transferred within the system itself, and if any transfers happen within the system, they do not qualify as work. So, what I see is in this case, if I consider both A plus B as my system, then the work interaction is essentially 0. So, there is no deformation or anything of that kind beyond the walls of this system. my system can be any arbitrary boundary. I am considering this plus this as my system. So, there is no work interaction. So, therefore, this is 0. So, then what I can see is my first law says, in this case it is du, and this is 0. So, my heat transferred will be equal to my change in internal energy. So, the Q will be equal to delta U. So, what I need to now do is to find out delta U. So, that is what I am going to do. Now, we have from the definition of specific heat, we have du is equal to, for an ideal gas, we have this as m into Cv into dt, that is our definition of specific heat. So, what I need to find out is find out the change. So, what was the initial state, what is the final state, and what is the difference is what I want to find out. So, let me find out, I know the mass of gas in A, I know the specific heat at constant volume, I also know the initial temperature, which is 70 degrees centigrade. For the gas in B, I know the mass, I know Cv, it is the same as here. I also know the initial temperature, which is here. So, the initial state, what I want is change in internal energy between the final state minus the initial state. So, what I am looking for is delta U between the initial state to the final state. So, at the initial state, I had gas over here which had Ma, it had a specific heat of Cv, it had a temperature of 70 degrees centigrade, which I am going to convert into Kelvin. So, let me do that right away. So, this is 70 degrees centigrade, which is 343 Kelvin. These are only differences. So, it is not always necessary to convert differences, but I am going to do it anyway. This is the initial internal energy, and the final internal energy I am going to call this as some T final, or actually we are already calling it as T2. So, this is the change in internal energy which we are looking for. I need to have a bracket here. So, Ma is 1 initially, Mb is 1 initially. The total mass does not change. So, when I take the sum, it will be whatever it was initially. So, over here I have 5 kilos into 630 joule per kg Kelvin into T2 minus T2 is also known here. So, T2 is 313 minus Ma1 is 1 kg into 630 into Ta1 is 343 plus Mb1 is 4, Cv is 630 joule per kg Kelvin, and Tb1 is 293. So, this is what I want. So, I can take out maybe 630 common. So, I get this value if I have done this correct. Let me just cross check. Okay. So, I get this value as 31500 joule, which is essentially 31.5 kilojoule. And from here I have that heat transfer, which is what I was looking for, is equal to this, that is also 31.5 kilojoule. So, this value is positive, which means that heat must be entering this system of A plus B when the mixing is going on. So, that is essentially what we see.